Everything's working. Okay. Hi, everyone. Thanks for attending my talk. I'm excited today to talk about TacTiles. This work was a collaboration between the AIT lab at ETHZ Zurich and the LMTS lab at EPFL. If this is working. Okay, well. TacTiles is a modular platform for building haptic VR and AR experiences based on a low-power electromagnetic actuator that you can assemble into a glove. And TacTiles allows you to explore object surfaces with your whole hand. And it can also render physical contact with virtual objects. And you can seamlessly switch between these two modes. So let me play a demo for you from the recent HoloLens announcement. But actually, to touch these holograms and seeing as how you can use any part of your hand to interact with them, what you might want is some kind of haptic device that can provide tactile feedback to the whole hand. And so what would be great, what would be needed to get great haptics in an AR and VR setting? Let's be a little bit more specific. What we want is something that can render realistic tactile feedback for extended periods of time in a light and conformal interface. And we can summarize these into high-level design factors. So by realistic tactile feedback, we mean something high fidelity, something that can render contact with objects or convey surface textures. And by light and conformal, we mean something that's wearable and something that doesn't stop your hand from flexing. And also we want something that's low power because then we can use this in mobile contexts and we can not worry about things like overheating. Let's look at 3 actuation technologies that are available to us today, but in terms of these design parameters. First, we have Vibrotactile Actuators. These are widely used in the industry. Everyone here is probably familiar with them. Today, this is a reliable technology that can be used continuously without worrying about things like overheating. And it's, of course, good for rendering things like textures we saw in the previous talk. And the main problem here is that Vibrotactile is not good at rendering contact with objects. Recently, research has attempted to improve the fidelity by using, for example, tilting and articulated platforms or textured spinning wheels. But these are not designed to span the whole surface of the hand, and they can be mechanically complex. Next, we have electrotactile actuators. These directly stimulate the mechanoreceptors of the hand and through electrical conductance. But similarly to Vibrotactile, they cannot render physical contact with the hand. Another promising technology is electromagnetic actuation, and this is with latching. And this is a technology we developed in MACTIX previously at our own lab. But the system was primarily designed for things like on-body notifications. So how does it fare in terms of the design parameters we established? The nice thing about this actuator is that you can actually render real physical contact with the skin. So it's high fidelity, and you can keep pushing on the skin without using any further power. And of course, it's wearable. However, the design was quite prone to overheating, and especially during rapid actuations. And what this means is that you can't render things like textures. And while it is wearable, it's a fixed pitch size, so you can't just arbitrarily place it around the hand. So it is a promising technology for VR, but it needs some work to get there, and this is where TacTiles comes in. So before I go on, this is kind of a quick primer on how electromagnetic actuation works with latching. First, there's a shielded magnet that's placed between 2 electromagnetic coils that's surrounded by thin latching plates. The latching plates are just thin pieces of metal that the magnet is attracted to. Next, a short pulse between 5 to 10 milliseconds is sent in one direction that causes the magnet to dislatch and move in the opposite direction where it's attracted to the other latching plate. And we can also reverse the current for it to go in the other direction. It's important to note that no further power is necessary in either state, which means that the design is bistable. Now, here's how we improve the core actuator in order to enable it for use in VR. First, we address the issue of overheating and pitch size by making each actuator a self-contained unit. And also, we reduce the size and weight by 50%. So now each tactile weighs only 1.8 grams and it's 1 centimeter cubed. We also use a custom 8-layer PCB, and this reduces the power consumption by 8 times. This allows us to achieve a sustained actuation rate of 2 hertz. That's twice per second. So you can activate this thing twice per second indefinitely. And we can also reach up to 200 hertz for short bursts, like for 50 milliseconds or so. For comparison, a single magnetic could be actuated only about 3 times per minute on average. And even with these reductions, we maintain the same latching force of about 160 to 200 millinewtons. Okay, once we started using the system in VR, there was actually an additional problem. So when you release an object in VR, you get this kind of, it's like super exaggerated, but it's an unwanted vibration. And what happens in real life is you don't get that vibration when you release an object. So in order to minimize these vibrations, we added damping material to one side of the magnet inside the chamber. And we also use asymmetric latching, which is that one latching plate is thinner than the other. Okay. Using an accelerometer, we tested 2 types of materials, foam and PDMS, and we found that they both significantly reduce vibration, although foam has a better exponential or faster exponential decay. You can see the paper for more details on this, and also you can read about the thermal, we did a thermal evaluation of the characteristics of the actuator. Okay, so we integrated 15 tactiles strategically onto the hand, and you can see that the hand can fully flex, and the actuators are not impeding the movement of the hand. Tactile supports 2 modes. The first mode is pulse mode. Here, the actuator doesn't touch your skin at all. This is like a single vibration of a piezo. We also have contact mode, where the pin actually goes through the glove and is touching your skin, and once it's touching your skin, it stays there without using further power. Next, we use pulse mode to render things like spatial haptic patterns. These are made to resemble, for example, explorations like feeling the texture of a piece of wood or sweeping your hand through the air so you can feel particles like snow or rain. And we use contact mode to render the sense of touch when you grab a mouse or a cup. And we use these modes and patterns to conduct a series of experiments to answer some questions. So in experiment 1, we wanted to see how well people can localize the actuators on the hand and which mode was activated. In experiment 2, we wanted to see how well participants could discriminate between different pattern frequencies, so how sensitive they are to the different patterns. I'll just play this quickly. And in experiment 3, we wanted to see if it's possible for participants to detect visual haptic mismatches. For experiment 1 and 2, we recruited 10 participants. This is the setup. And we seated them in a quiet room. They wore noise-canceling headphones. In experiment 1, a random location was played on the hand, and they had to kind of point to that piece of paper and tell us which one it is. For experiment 2, there was 2 virtual surfaces, and they had to test each surface and say which surface had a pattern that was playing faster than the other one. And we used this, we used a staircase, an adaptive staircase procedure to calculate a just noticeable difference. So moving on to the results. The mode accuracy was actually quite high. However, participants struggled with localizing the stimuli. So for example, around the base of the fingers and the palm, they had a hard time telling, getting a high localization accuracy. For example, even the middle finger and the index finger, they could get it confused. It was also really interesting to see that participants could differentiate as little as 3% difference in pattern frequency. And just for reference, this difference here that you're seeing visually, that's 20%. So haptically, they can sense 3%. You can see the paper for more details on these experiments. In the third experiment, we set up a kind of a haptic playground where participants could explore surfaces, object surfaces, and make contact with objects. And here we recruited 6 of the 10 participants from the previous experiment, and they wore the TacTiles glove and an Oculus headset, and they wore noise-canceling headphones. Of course, we also wanted to test some things. So we set up a scene that had some visual and haptic mismatches in terms of direction and in terms of frequency, and also some objects they can make contact with. So I'm going to present some takeaways from the experiment, and this is going to be in the form of participant videos. So hopefully you should be able to hear it. Okay, so here a participant was presented with conflicting stimuli in terms of visual and haptic patterns.
The very left wood block, it kind of goes like this, right? and the middle one goes like this.
Okay, so this participant is not only able to tell that there is a mismatch, but also that the directional difference is actually perpendicular, so they could sense that. It's also interesting because this result conflicts with related work, where they applied different directions on a single finger. But here, when we have haptic feedback on the whole hand, then the direction starts to matter. The next video is pretty interesting. This is a participant who tries contact mode for the first time. And I just want to note that this participant actually has quite a bit of VR experience and even haptics in VR experience.
This is very penetrating, but very convincing. I have the feeling I touched an object.
Right, so we didn't actually ask participants to compare the two modes, the pulse mode and the contact mode, but they did anyways, and most of them actually liked contact mode. And as you can see, the sensation was very convincing, but I think the challenge is actually how to tone it down. So in the future, we can work on this. And finally, as a bonus task, we also asked participants to see if they could locate a mouse on the table, it's off screen, by using their sense of touch alone. So you can see how this participant is going to kind of slide their hand over the table, and then you will see that the kind of pattern indicator will light up blue once they find it. Yep, they found it. So actually, 4 of the 6 participants could find the mouse by touch alone on their first try. And this is an example of a new kind of interaction that's possible when you combine both modes of actuation. Of course, there's some improvements that can be made. The biggest limitation is probably the lack of pressure levels. We only have on or off, essentially. And this would be actually very tricky to implement because in order to do that, we have to remove the latching technique. And so you would have to keep applying pressure onto the skin, and to do that you have to supply constant power, and then this could cause overheating and so on. So it's quite tricky. And then the next thing we can do is we can kind of increase the realism for grasping if we combine tactiles with the kinesthetic solution. So this is something we developed previously at our labs as well. This is a technology called dexterous, and this is based on electrostatic actuation. And both technologies are designed to be low power and light, and then combining them together, I think, is a natural fit. So to summarize, TacTiles is a wearable. Let me just mute that. It's a wearable and conformal tactile interface which has 2 modes of actuation, and these are pulse mode and contact mode, and it can be actuated 2 times per second indefinitely. And by retaining the most important characteristics of piezo's, the small size and the low power, it allows us to scale in the same way that piezos do, into larger systems like the TacTiles glove, and we hope many others. Thank you for your attention.
So we have time for 1 or 2 questions. Okay, so then I have the first one. Okay, have you tried different configurations for the actuators, like on the hand, like having more or less actuators, or do you know the ideal number?
Yeah, it's a good question. So what is the optimal density for such a glove? I mean, the size allows us to definitely have more. We kind of had an interface that was limited to 15, so we did try some alternative locations. These locations were actually from a reference that we found that tested like 120 of these locations, and they determined which locations were the most effective for determining which grasp to use. So they were kind of sourced from a location. But I think, yeah, increasing the density probably would help with some tasks. Yeah.
Okay, and it will not like improve like the flexion of the finger. We need to put some more actuators.
Yeah, so it's true. Yeah, of course. Like if you could add 50% more actuators, and at this point, once you start adding more and more, they would kind of start hitting each other. So, yeah, it's there's some limit in the way that the current size of the actuator is. Yeah.
Any other question? Okay, a last question for me.
Okay, sure.
I have another one. And then, have you tried like to test if people were able to discriminate like global shapes, like for instance on the mug, like
Right, yeah, that's actually a great question. That was one of the original kind of intents of the project, was to see if people can feel like a sphere or a cube, but it's very tricky because how to say, the order of the activation really matters in this case on the shape of your hand. So if you were to grab kind of this microphone, right, so you would expect that the middle part of your hand touches and then this hand and then the outer part, right? So, but if you can go through the object, there's no guarantee that this order will repeat. So it's very easy for someone to just get a random sequence and it won't mean anything. So no, you can't. Yeah.
let's thanks again the speaker.